Hello, Physics 2. So hopefully all of you have found the Supplemental 3 chapter. I have posted it to Blackboard. It's also available on the Matter and Interactions website. It's a free PDF download. All of the answers for the problems in it are at the back of your book. And basically what this is all about wave propagation. So we're going to build on what we have covered mostly in chapter 23. It also builds on chapter 4 material because wave propagation is true for both electromagnetic waves but also other types of waves. So some of these principles have been true all throughout, and you're going to see some really similar formulas that you have seen before. And this is because the beauty about waves is they're just mathematically stunning to describe, and they're beautiful, predictive, oscillatory natures. So, starting supplemental 3. No, we're not getting any further than some distance through this chapter of some undetermined amount. All right, so in this chapter, we are going to study waves in more detail. So, wave phenomena. All right, so something to know about waves. Waves are the mechanisms for how energy travels. This is true for light, and this is true for sound. Or any other type of wave. So, for example, you can hear that very loud banging sound because the energy of my pen striking the metal is propagating through in the form of compression waves or sound waves. I can also take a spring, which I've kept handy dandy right here, and I could move it back and forth. Oh, this is going to be a difficult way to, let's see. Yeah, there we go. You can see I'm putting a wave in it poorly. There we go. And you can see that wave going through that spring is propagating the energy from my hands. So it's traveling from one side to the other. You can see those vibrations. All the result of energy propagation. For the thing I like about springs, you can also get a good compression wave going on. So I'm just sending waves through like that. And of course, this is how we make music. That would not be music that I was doing on that spring, but all right, so we're going to start by focusing on electromagnetic radiation. So, let's talk about a couple aspects of waves. So first of all, there's a variation in time. So maybe you're here, and then let's see, some green light, maybe 5:50, eh? And light goes by. Light goes by and still I think of you. Oh, nobody knows that song that came out in the early 2000s. All right, so you can see light goes by, and you can see that you will observe an electric field with a variation we'll have E cosine 2 pi t over t. So this is the phase. So on this axis, we've got our time axis here. And this is different from the period, which is how long it takes for the wave to go up and down once. And so if you have a light wave, you're seeing this type of variation. Now, to be fair, our eyes are not that sensitive to be able to discern this variation, but you could measure this with an instrument in a lab. And so building on this, the phase will increase by 2 pi radians, which is 360 degrees, whenever t increases by amount t. And this makes sense. So if we think about it in terms of our light wave, so we start, all right, now we've done a full transition, so we've increased the phase by 2 pi. That is a period of t that has passed in time t here, and then this would go on just like that. So every time you roll over a full transition, so you would change the phase by 2 pi radians or 360 degrees, and then this would happen in amount of the period t. So. Okay. Also something to note, so we've been talking about a time varying E field. Note, there is also a time varying B field, where B is perpendicular to E. So this is still true where you have your electric field and your magnetic field, and then your direction of propagation, like that. However, it's the electric field that we tend to measure. So if you remember when we compared the different strengths of the two fields in terms of measurable quantities, the E field is going to be what you notice, and it has the greater impact. So we focus on the electric field, it has a greater impact. But it doesn't mean that the magnetic field has gone away. It's still there. Greater impact. Okay. So now that we understand our variation in time, let's think about the variation in space. If you want to make anything sound cool, just add in space at the end. I mean, like, there's this really awesome experiment called LIGO, which is a laser interferometer gravitational wave observatory. And they measure gravitational waves from space using lasers. Very cool. I've seen the LIGO experiment. So cool. Well, there is a proposed experiment called LISA, laser interferometry in space, where they would do the same thing, only they would put giant lasers in space to measure gravitational waves. How much cooler does that sound? Sounds so much cooler. Oh my goodness. But they keep changing their mind as to whether or not they're going to give that experiment funding. So I don't know if we'll ever see it, but boy, does it sound cool. All right, so I digress. In addition to varying in time, the electric field from light waves will vary in space because they want to sound cool. It's the only reason why. I'm kidding. So the space variation can be expressed as E cosine 2 pi x over lambda. So once again, we see our phase, that 2 pi over lambda, and then x is corresponding to the space variation. So essentially, let's draw some pictures. So now we're dealing with that space variation. So we can look at this wave because it will propagate through space, not just time. And so looking at our electric field. And now this axis is the x-axis. So we're just going to focus on, we'll just say that this is an x. So, okay, so from peak to peak, you have lambda. You get 1 lambda in a period t. It's going at some velocity v. If it's electromagnetic radiation, it's likely going at the speed of light, unless you've slowed it down by refracting it through something. Or maybe you're in a slow light lab. Way cool. All right, so once again, we can see a lot of similarities between the time variation and the space variation. So let's go ahead and note them. So note the similarities. So in time, the electric field, or the E field variation in time, is equal to E cosine 2 pi t over the period capital T. So this, it's going to propagate through one phase in period t. And then the variation in space, or x, E cosine 2 pi x in lambda. So it's going to go through one wavelength in the distance x. So when x is equal to lambda, then you've gone through one more phase. And you can actually bring both of these together. So we can express both time and space variations in one expression. So you have E of xt, so we're going to look at both the space and time variations, is equal to E cosine 2 pi t over the period capital T minus 2 pi x over lambda. And as the time increases, you need a larger x, so it's going to travel through more space to get the same total phase. And this makes sense. Light travels through time and space. You travel through time and space. Time just happens to constantly move around you. So this is a concept that, should you choose to go further within the field of physics, is you will start to bring in this idea even further, that you're not just traveling through space, but you are traveling through time as well. So when you think about space-time, a four-vector approach, that's essentially what we're looking at, is where we are factoring into the equation that it is, you travel distance in time. And so that needs to be a part of how we think about things. Okay. So moving on into a phase shift. So not all waves start at the maximum value. In fact, you can kind of choose to start your problem wherever you want. So far, every picture I have drawn has looked like this. Where that would be t equals 0, so they don't, not just here. I mean, you could have a wave that's starting there, or maybe a wave that's starting here, or a wave that's starting in there. It doesn't matter. You can put your t not wherever you want. You choose any point, and you'll do it for strategic reasons if you're solving a problem, to be your t equals 0. This is on you. So, if, for if t equals 0, then you could have this expression, 2 pi t over t minus 2 pi x over x, not necessarily be at a max. So this may not be at a max. And so that's going to more correspond to this term, because this term will be 0 because t is 0. So therefore, you would need to update this with a phase shift. And conventionally, we denote phase shifts with phis, which basically means we did not start this wave at a maxima, therefore we will adjust for that. Use, so our Greek letter phi, to denote a phase shift. And phi can have values between 0 and 2 pi. And so you could really think of phi always being in the equation. It's just sometimes it's equal to 0. All right, so I'm building on that. If the phase difference between two waves is 0, then these waves are in phase. So let me just give you a big hint. These waves here are not in phase. None of them are in phase with each other. You see a big tangled mess of waves up there. But if I had, say, to rely on my awesome drawing skills, this wave like here, and then I'll just, so in this case, I'm drawing them separately, but these two waves would be in phase. starting and stopping at the same place. So, and then if there's a phase difference, then they're said to be out of phase. So if there is a phase difference, so basically phi is not 0 between them. 2 or more waves, then they're out of phase. And I'm not going to redraw. When I have this lovely multicolored image, I can just show you again. So very out of phase waves, clearly out of phase. Okay, so moving on to more wave properties, we can talk about angular frequency. So we can rewrite our energy equations in terms of angular frequency, which we first saw in chapter 4. Way back in Physics 1, when everything was new and exciting, maybe sometimes a little bit scary, but look at how far you've come. Seriously, I really recommend, like, go back and look at Physics 1 material and just be like, oh my goodness, I've learned so much this year. This is incredible. I used to do that from time to time when I was in physics, like, oh man, I feel like I don't know anything. I mean, I didn't know anything. I still don't know anything. My field is huge. I will never know anything, no matter how much I study. But sometimes I look back at, like, everything I've learned. I think, wow, that used to be hard. I can do that now, easily. This is really cool. And you should take the time to do that for yourselves as well. You've learned a lot. All right, so e cosine 2 pi t over t plus that update for the phase shift. So this is a basic form. And we're now looking at just the e of t. So frequency is equal to 1 over the period. Therefore, e cosine can be updated to be 2 pi frequency times t plus phi. And omega is equal to 2 pi times frequency. So then you can update this to be e cosine omega t plus phi. And if you'll remember, omega has units of radians per second. And this is something we have seen many, many times before. So we saw this first in chapter 4. This is really the form that you tend to see a lot of wave equations written in. So e cosine omega t plus your phase shift. And for those of you that have taken differential equations, I think that's just one of you, you've seen this before. So differential equations is basically all the math required to do stuff like this in more detail. There's a reason, I know I've said this many times, but there's a reason why differential equations classes in places that have physics majors will be full of physics majors. So when we took, I took 2 semesters of differential equations. The first semester was half math majors, half physics majors. The second semester had 1 math major, and everybody else there was a physics major. Why? Because we need it. We do it a lot. All right, so intensity. Intensity is the time averaged energy flow of an electromagnetic wave or waves. So at one instant in time, the electric field is E cosine omega t, and instantaneous energy flow is proportional to E cosine omega t squared. All right, so I'm going to do a series of stepping through the relationship between what we've covered. We talked a little bit about intensity at various points in subsequent chapters, primarily in chapter 23. So I'm going to tie in intensity with our new wave expressions that we've been playing with. All right, so I'm actually going to redo this because I want to keep these equations together. So we have E cosine omega t and energy flow is proportional to E cosine omega t quantity squared because the time average flow is proportional to E squared, which we talked about in chapter 23. Intensity is measured in watts per meter squared. So recall the recent past of chapter 23. And intensity, therefore, is proportional to the area squared. And so intensity is proportional to E squared for electromagnetic radiation. And the intensity basically is the brightness. So not just do you see light, but how bright is the light that you're seeing? By the way, I did an experiment once where we related the intensity of the radiation we were producing to the density of the gas that we were focusing it in. So cool. And intensity in terms of a sound wave is going to be loudness. And I am strongly considering, I've got some simple slides on waves and sound waves, and I think I'm going to get them up for you guys. They are other stuff that I did for a physical science class, but I personally think sometimes that there's always a benefit in having some basic breakdowns. There's also some really nice pictures in those slides. All right, so interference. So we can use the superposition principle to understand electric fields from waves too. So the superposition, that's supposed to be, the superposition principle basically is that your net field is going to be the sum of all of the fields within a particular area. We know that electromagnetic radiation, like light, basically means that you've got electric fields within that area. So if you're summing fields together, you need to account for the E fields from light. So in this case, your net electric field is the vector sum of all the E fields from all the sources. And this works just fine if they're varying in time. And we actually already sort of drew some superimposed fields. So for example, we've got some orange light that we're adding to some blue light. So you would just add these together. So, and in this case, so we're moving towards analyzing two interfering waves. In terms of E field summation. So that is what we're working towards. Okay. So where this becomes a really simple way to see this is in laser alignment. So I have aligned a lot of lasers. Well, not as many as some people I know. But in laser alignment, basically what you're often doing, if you have an interferometer, so like a Mach-Zehnder interferometer or Michelson-Morley interferometer, you're going to overlap two beams, and you're going to see how well they've lined up. You're going to look at these two beams which have been overlapped, focus the light through a slit, and you're going to see some interference patterns. So which is basically going to be spots of light and dark. So I'll write this down. If you overlap two beams or shine a light, you can observe interference patterns with just a coherent light source through two slits. You will see an interference pattern. And it looks something like this. Lines of light, dark. They might be a little bit thicker, it depends. You're going to use some lenses to focus them to get a nice clear picture of these interference patterns. And you can learn all kinds of things from them actually, like densities and whether or not your lasers are aligned, and very useful. Very, laser alignment is an art form. That's all I will tell you. Some people are good at it, some people are excellent at it, and some people who are brilliant physicists are terrible at it. I fall somewhere in the middle of this spectrum, but I have worked with some people who couldn't align their way out of a paper bag, who were incredible physicists. And they would ask me how I would do it, and I would say, I can't tell you, you just have to have a sense of it. And I taught one of my best friend in the field is a laser physicist, and we've talked about that. I'm like, yeah, I really can't explain why it is that this works. And she'll say the same thing. Yeah, you just kind of know what you need to do. All right. So you can think of this in terms of water wave interference. Think water wave interference. And so these patterns exemplify the wave theory of light. So when you see these interference patterns, they're really showing off that light is wavelength and light is particle-like. I mean, it is particle-like, but that's not a proof of the particle-like nature. So, for example, when you've got water waves, you've probably seen like a boat going forward, and you'll get something like this in the water. That's what the picture that I want you to recall. Okay, so going back to the light and dark spots. So we can use the superposition principle to predict dark and bright spots. So all light can give you an interference pattern, but lasers are particularly useful. But it's very obvious with lasers. And here's where I would ask, does anybody know why? But if anybody answers right now, that would be frightening. That's because they have coherent monochromatic radiation. Basically, you've got one nice long beam of light that doesn't thicken unless you put it through lenses to make it thicken. It is all one wavelength. Laser physics was discovered in, I believe, the 50s, and it has just revolutionized our world in ways that is just beyond our wildest imaginations. So same phase, same wavelength. That's the beauty of lasers. If you need to make a precise measurement, you want to use a laser. That is what they're there for. So there are two different types of interference. You can have constructive interference and you can have destructive interference. So constructive interference basically means you're going to make it brighter if it's light, or louder if it's sound. So what if we had two parallel radio antennas? Then I would hope we had a radio station. So they have the same transmitter, same electric field. They both have this E cosine omega t and same omega for both of them. So but they're parallel, so really so we have this. Okay, so you can see all the peaks are lining up with all the other peaks. It's hard to draw two things that are parallel. So they're next to each other. We're just kind of looking at them at a weird angle. Okay, so for each one of the, oops, I've drawn them in colors. Let me put them in colors. So for each of these peak alignments, you would have, I've done a terrible job of adding these together. E1 plus E2. And so these two waves are crossing each other in phase. And so you'll get twice the electric field, essentially, at each and every single one of these peaks. They are constructively interfering. So two waves crossing in phase yields E cosine omega t plus E cosine omega t is equal to 2 E cosine omega t. So this is constructive interference. And in terms of light, so those fringe lines that I showed you, the bright spots, are constructive interference. So that is how that works. All right, so if you have constructive interference, you can also have destructive interference. So let's say those antennas are out of phase, 180 degrees. So you would have so basically everywhere red goes down, blue goes up, blue goes down where red goes up. Okay, so at any given location, one wave has traveled lambda over 2 further than the other. So when you add these two up, you get E1 plus E2 is equal to 0. And so in terms of light destructive interference, that means total darkness. And you can also see this in different types of waves as well. So basically, the two waves are canceling each other out. All right, that wraps up Thursday's lecture of week 16. Since the slides ran over long, there's not going to be a part 2 because the 2 times should average out to about the same time that we would spend in class.